When we think about the power grid, we usually picture the big stuff, right? Massive generators, humming transformers, power lines stretching to the horizon. But behind all that raw power, there's a hidden world. A lightning-fast defense system of silent guardians that keeps the whole thing from tearing itself apart. And today, we're pulling back the curtain on them.
I mean, seriously think about that question. A short circuit inside one of these generators can unleash a catastrophic amount of energy, enough to cause an incredible amount of damage almost instantly. The answer isn't a person with their hand on a big red button, it's an automated system that works with unbelievable speed and precision.
So, here's our game plan. First, we'll get into the core philosophy of these guardians. Then, we'll meet the 5 key shields that protect the generator itself. We're going to dive into what I call the battle of the currents, then look at how we guard against sneaky threats like ground faults and heat. We'll cover the backup plan for when that first line of defense fails. And finally, we'll see how it all connects to become the grid's incredible nervous system. All right, let's step into the shoes of a power system engineer. To protect these massive, expensive machines, you need more than just good hardware. You need a really smart philosophy of defense. This is the key concept: protective relaying. Now, don't let the formal definition fool you. Think of it as the senses and reflexes of the entire power grid. A relay in this world isn't just a simple switch, it's a tiny digital brain that's constantly monitoring the system's health. It's programmed to make life-or-death decisions in a split second to isolate a problem before it turns into a catastrophe. Now here's where it gets really interesting. This is the core philosophy from our source material. And it might sound a little crazy at first, right? But trying to build a system that never fails is basically impossible and astronomically expensive. So the smarter approach is to accept that, things will eventually go wrong, and instead you pour your resources into building an incredibly fast, intelligent system to contain those failures the instant they happen. That's what makes protective relaying the real hero of this story. So how does this all work in the real world? Well, the system uses layers of defense, but we're going to focus on the 5 main shields that guard the very heart of the generator, those big copper coils called stator windings. That's where all the magic, all the electricity is actually made. And here they are, our 5 key shields. You've got differential and split phase protection, which are all about watching for dangerous imbalances in the electrical current. Then there's stator ground fault protection, which is basically looking for electrical leaks. And of course, overheating protection, which is pretty much what it sounds like. It's the generator's built-in fever detector. So let's break these down.
The first 2 shields are all about winning what we're calling the battle of the currents. They're designed to spot the exact moment when the immense electrical currents flowing inside the generators start to go rogue.
The number one threat here is an internal short circuit. This is when electricity decides to take a shortcut it's not supposed to, right through the generator's windings. When that happens, it releases just an enormous amount of destructive energy. This is the kind of thing that can cause a total failure in milliseconds.
And the solution for this it's brilliantly elegant. Differential relaying works on one simple, beautiful principle. What goes in must come out. It uses these precise sensors at both ends of the generator's windings, and you can think of them like super accurate digital meters for electricity. They're constantly comparing notes. If the number of amps going in doesn't perfectly match the number of amps coming out, the relay knows instantly that current is leaking somewhere in the middle, and bam, that's our short circuit. It trips the breakers immediately.
And the stakes here could not be higher. As our source material puts it, pretty bluntly, if that relay fails to do its job, severe thermal damage is pretty much a guarantee. We're not talking about a small problem. We are talking about a multi-million-dollar piece of equipment literally melting itself down from the inside out.
Okay, now for a much more subtle threat. Imagine a giant spool of copper wire, just wound perfectly. A turn-to-turn fault is when just one of those little loops of wire touches the one next to it, creating a tiny short circuit. It's a small failure, yeah, but it's one that can unravel into a huge disaster if you don't catch it early.
This is where split phase protection comes in. It is incredibly sensitive, able to detect even a single shorted turn. It does this by comparing the currents in parallel winding paths. But here's the really clever part. It uses an intentional time delay. This lets the relay ignore those brief, harmless little power surges that happen all the time, and only act when it sees a problem that sticks around, which tells it, hey, this is a real fault. All right, let's move on to our next set of shields. These guys are guarding against 2 totally different kinds of threats: electricity leaking where it shouldn't, and the simple, destructive danger of just too much heat. A state or ground fault happens when the insulation on a winding fails and current literally escapes into the steel core or the frame of the generator. This is actually a very common type of failure, and it can cause some serious damage if you don't clear it fast.
So how do you catch a leak like that? Well, the preferred method is really ingenious. You connect the generator's neutral point to the ground, but you do it through a small transformer. Normally, zero current flows through this path, but during a ground fault, that escaping electricity rushes to the ground through that transformer. A relay is watching that transformer, and the second it sees that abnormal flow, it knows there's a problem and sounds the alarm.
The next threat is something we can all understand: overheating. This can happen for two main reasons. Either you're running the generator way past its limits, or, and this is critical, the complex cooling system, whether it's air, hydrogen, or water, has failed. Now, you've got two main ways to protect against this, but one is clearly way better. So-called replica-type relays try to guess the temperature based on how much electricity is flowing. But the preferred method, using temperature detector relays, measures the actual temperature inside the windings. And here's why that matters. A replica relay can't tell if the cooling system has failed if the load is normal. But the direct temperature detector, it doesn't care about the load. If the cooling dies, it sees the temperature creeping up and it trips. It's the difference between guessing someone has a fever and actually using a thermometer.
Okay, so we have all these amazing shields acting as our first line of defense. But what happens if one of them fails? What if a relay just doesn't operate or a circuit breaker physically gets stuck? Well, the system has a plan for that too.
This is the whole concept of primary versus backup relaying. Primary relaying is everything we've been talking about so far. It's super fast, it's precise, and it only disconnects the one piece of equipment that failed. Backup relaying is the second line of defense. It's designed to be slower, on purpose, to give the primary relays a chance to do their job. If they don't, then the backup system kicks in. The trade-off is that it's way less precise. It has to disconnect a much larger chunk of the power system just to be sure the fault is cleared. But hey, that's a whole lot better than an uncontrolled failure.
And this quote from the source material is just a vital piece of wisdom. A backup system is an absolutely essential safety net, but it is no substitute for doing proper, regular maintenance on your primary protection. If you have to rely on your backup system, it means you're already having a very bad day.
Okay, let's zoom out and pull all these pieces together and really look at what this whole system of silent guardians represents.
When you look at all these relays, all communicating and acting in perfect coordination, you realize it's not just a collection of fancy switches. It is a high-speed autonomous nervous system. It senses pain, a fault, and triggers a reflex in thousandths of a second. It's making these critical decisions that protect billions of dollars of equipment and, more importantly, preserve the stability of the power grid that all of us depend on every single day.
And that leaves us with one final big question. Our electrical grid is changing. It's getting more complex with new energy sources, new challenges. So the question for the future is this: how will these silent guardians, these incredible protective systems, have to evolve to keep watching over it all?